5, exponential and logarithmic models. So we're dealing with multiple equations today. You've got to understand when to use what equation, and it's a matter of plugging the right numbers in at the right time. That's all it is, plugging numbers into equations. So objectives: recognize the 5 most common types of modeling involving exponential and logarithmic functions. Use exponential growth and decay functions. Use Gaussian functions to model real-life problems. Use logistic growth functions to model and solve real-life problems. Use logarithmic functions to model and solve real-life problems. So word problems, formulas, here are the 5 formulas. You have your exponential growth model. Does that one kind of look familiar? Y equals AE to the BX. What's it kind of look like? Kind of looks like PERT. So growth, B is positive. Decay, look at how that's written. Y equals AE to the negative BX, where B is still positive. So you're plugging in positive values of B, but there's a negative built into the equation, okay? So anytime you see that negative exponent up there, what does a negative exponent do? It turns it into a fraction, right? So if I have 7 to the negative 1 power, that's 1/7, right? So obviously it's going to get smaller by a factor of 1/7. The Gaussian model, look at there, you got an exponent and then exponent on the exponent. That's a beautiful thing.
Is that 2LC or 2?
That's 2 divided by C.
I feel like that's hard to.
Okay. You have your logistic growth model. That's going to be your bell curve. And you have your logarithmic models. And that's what we're dealing with today, those 5 equations. Okay, slide known. The basic shapes of the graphs. Here's what so you've got 5 different functions, and here's only three graphs. These 3 graphs is what those 5 functions look like. Obviously, the first one's going to show you exponential growth. The second one's showing you exponential decay. And the third one's showing you a bell curve or a Gaussian model. Some more graphs, your logistic growth model, your natural logarithmic model, and your common logarithmic model. Natural log and common log, pretty much the same shape, right? Just different bases. Yep. You often gain insight into a situation modeled by an exponential logarithmic function by identifying and interpreting the asymptotes. What's an asymptote? Okay. It's an imaginary line that a graph approaches, right? Can't really say never touches because there are cases where horizontal and slant asymptotes can be crossed. Okay. But regardless, in behavior of the function will be approaching that asymptote. And it's actually possible for a graph to cross a horizontal asymptote or slant asymptote infinitely many times. Like this is an asymptote, and I had a graph that was kind of going like this, but as it went further, it gets closer and closer and closer to the line. It's still crossing it over and over and over and over. But in the end, it's going to look like that line. We're going to identify the asymptotes of the graph of each function shown previously. Okay, so let's go back to the previous 2 slides and look for any asymptotes. Exponential growth. Does the exponential growth model have an asymptote? You think there's one at 2? Okay, and that would be no, because x can be any value. Okay, so 2 is not an asymptote. Are there any asymptotes for exponential growth? Yes, we have a horizontal asymptote at y equals 0. How about exponential decay? Same thing. Think about it. Exponential decay. Something's decaying. Theoretically, it decays forever. Does it ever go away entirely? No. Okay. So we have a horizontal asymptote at y equals 0. How about the Gaussian model, the bell curve? Okay. We also have a horizontal asymptote at y equals 0. So as x approaches negative infinity and as x approaches positive infinity, we have the graph approaches 0. Next one. Logistic growth model. Do we have any horizontal or vertical asymptotes? Okay. This particular function does have 2 horizontal asymptotes. We have y equals 0 and y equals 3. So what's happening here, as the value of x approaches negative infinity, the denominator is approaching infinity. So you've got 3 divided by 11 million. That number is going to be all right, approaching 0. However, on the other side, as x approaches infinity, the value of this is also approaching infinity. 0. So you got 1 plus 0. 1 plus 0 is basically 1. So that's why it's 3 divided by 1. So that's approaching 3. Natural log model. We have a vertical asymptote. Where? I want the equation. X equals 0. That makes sense, doesn't it? If exponential had a horizontal asymptote and these guys are inverse functions, then logarithm has to have a vertical asymptote. And common log, same thing, right? Any questions about these asymptotes? Okay. And that's what we just did. Estimate the amounts in billions of dollars of U.S. online advertising spending from 2011 to 2015 are shown in the table. So what's happening to the money spent on advertising and online ads? It's growing. Is it linearly growing? Okay. It's safe to assume it's probably exponential. Okay. Move on. Here's the graph. Does that kind of appear to be exponential? Does it appear to be straight? Slight curve, right? Slight curve. Okay. So it is exponential, and they actually give us the equation. So the spending is equal to 9.30 times e to the 0.1129 t, where t is some value between 11 and 15. 11 represents 2011, 15 represents 2015, and so on. Just facts right now. Bless you. Here's the question. Compare the values given by the model with the estimates shown in the table. So the table data is factual data. That's the given amounts, okay? Using those given amounts, they came up with the equation. This question asks us to fill in the numbers into the equation and see what we get. So if you plug 11 into the equation, what do you get? And since we're doing this 5 times, would you want to type this 5 times? Y equals best bet, right? Okay, how do you feel about 32.2 compared to 31.3? You get, what did you say, 32.2? The book's answer says 32.2. How do you feel about your answer? Pretty close. Yeah. How about 2012? Okay. So look at these and we keep going. Does that model appear to be a good estimator of what's going to happen? Okay. All right. So the next part of the question says, according to this model, when will the amount of US online advertising reach 80 billion? So where does the 80 go into our equation? The S, right. So let's go ahead and work this out. So if S is 80, we get 80 equals 9.3 e to the 0.1129 t. Okay, let's solve for e. What should we do? I solved for t. What should we do? Not yet. Not yet. Divide by 9.3. You can't do the log until you have the e by itself. Okay. So dividing both sides by 9.3 is probably going to be an ugly number, right? 8.6. So 8.6 is equal to e to the 0.1129 t. Okay. Any specific log? Yeah, we're dealing with e, so let's take the natural log of both sides. So natural log of 8.6 is equal to the natural log of e to the 0.1129 t. And why do we take the natural log? Cancels out, and it's going to bring that out of the exponent, right? So I now have natural log of 8.6 is equal to 0.1129 t. Next step. Okay, so t is equal to natural log of 8.6 divided by 0.1129. And t is about 19. Okay. Now, since you've already typed this equation into your y equals, does that match? If you look at your table and you went to 19, does that put you pretty close to 80? Okay. But you got to understand the algebra and how to work this. Questions? Here's the next slide where they worked it out. They went ahead and did the natural log and they're writing the approximation. Next slide. 19.1. So according to the model, the amount of US online advertising will reach 80 billion in the year 2019. Questions on that? A living organic material, the ratio of the number of radioactive carbon isotopes, carbon-14, to the number of non-radioactive carbon isotopes, carbon-12, is about 1 to 10 to the 12th. Big number. When organic material dies, its carbon-12 remains fixed. However, radioactive carbon-14 begins to decay with a half-life of about 5,700 years. Y'all have heard of carbon dating, yes? Okay, that's what we're talking about right here, okay? What is half-life? It's not a video game. What is it? What's that mean? What does half-life mean?
Every single year it goes away by half.
Not every single year.
500.
Okay. For this particular radioactive substance, it's going to take 5,700 years for half of it to be gone. And 5,700 years for half of that to be gone. And 5,700 years for half of that to be gone. This is exponential decay. It's going to start going pretty fast, right? But when you start taking half of a 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 half, right? It kind of looks to the point like you're not taking anything away. So there's the problem, or the information for our problem. Here is what the graph of this might look like, or does look like. To estimate the age of dead organic material, scientists use the following formula, which denotes the ratio of carbon-14 to carbon-12 present at any time in years. They did some calculations to figure out what this value was up here. This value is negative 1 over 8,223. We'll do that in a little bit. So here's the given formula. So the graph is shown at the right. Note that R decreases. So as we increase in time, the amount of the radioactive substance is decreasing. The value of B in the exponential decay model, y equals AE to the negative BT, determines the decay. To find how much of an initial 10 grams of, I think this is radon, RA, is RA radon? Any chemistry experts? The 226 isotope with a half-life of 1,599 years is left after 500 years. Substitute this information into the model. So we know the equation. Somebody's going to say something? Radium. Thank you. Here's the equation. We don't know right now what B is, but we need to figure that out. We do know the half-life is 1,599 years. So I want to know how much is left after 500 years. So 500 represents T. We start with 10 grams. So in one half-life, how much is going to be left? If we start with 10, 5 would be left, right? Okay, so here we go. So Y is the amount afterwards. So Y is going to be half of 10. The amount we start with, A is 10. E to the negative B, we don't know what B is right now. We need to figure that out. We know time is 1,599 years.
So we're plugging the 1/2 of 10.
Yes. Yes. Okay. So here's the equation we start with. We have 1/2 of 10 equals 10 e to the negative 1,599 b. Dividing both sides by 10 makes the 10 go away, right? So half of it is left. E to the negative b is 1599. How do I get the exponent down? Natural log of both sides. So that's what they're showing here. So the natural log of 1/2 is equal to negative 1,599 b. To get b by itself, I need to divide both sides by negative 1599. So b is equal to negative natural log of 1/2 divided by 1,599. Now that I know what b is, I can do things with this problem. So using the value of b found from above and a equals 10, the amount left over is, and here's the equation. So this is supposed to be a y. Okay, so y equals 10 times e to the negative b. Remember, B was negative. Okay. So negative, there's my B, there's my 500. And you can actually type that right there in your calculator, as ugly as it is, and you get 8.05. Any questions on this equation? As mentioned at the beginning of the section, the Gaussian models are of the form y equals ae to the negative x minus b squared divided by c. In probability and statistics, this type of model commonly represents populations that are normally distributed. The graph of a Gaussian model is called a bell-shaped curve, and we're doing lots of this in stats right now. Try graphing the normal distribution with a graphing utility. Can you see why it's called a bell-shaped curve? I can't do it divided by C, so we can't really look at that in the calculator right now. For standard normal distribution, the model takes the form right here, 1 over the square root of 2 pi e to the negative x squared divided by 2. Graph that. Actually look at the graph. Now that you can't see it. You can see that, can't you? Okay. So maybe if I change my from -5 to +5, counting by ones, from -1 to 3, counting by ones. That's a little more. In a bell curve, let's see what. So a bell curve looks like this. What's that? This is going to be your average. So if we were looking at ACT scores or SAT scores, that's going to be the average. Your high performers are going to be over here. You have a lot of high performers. Your low performers are over here. Do you have a lot of low performers? So that's how a bell curve is built. Okay. All right. And then we do standard deviations and.
It's for
Used for what? What's an antigen?
is the thing that causes inflammatory.
That's why I'm hurting.
No, it stops infection.
Oh, okay.
No, they're the things that mark.
Oh, SAT scores. Here we go. In 2011, the SAT mathematics scores for high school graduates in the United States roughly followed this normal distribution. So here's the equation of the normal distribution of math SAT scores in 2011. X is somewhere between 200 and 800. Higher than 800 on the SAT? No. No. 800 is a perfect score. And I think if you put your name on it, you get 200. So X is the SAT score for math. Sketch the graph of this function. From the function, estimate the average SAT. Where's the average happen? In the middle, okay? So I'm gonna pull this over here. Okay. So Y equals, clear that out. 0.0034 E raised to the, I'm just going to type it the way they do and not have to worry about doing the fractions. X, that's the 2, 800 plus 800. Do what?
Like the actual, like this sign, not the minus sign? Like the negative sign?
Did I hit the negative sign? I hit subtract. Thank you, sir. It would have given me an error in a minute. X minus 5 squared divided by 0.378. Enter. What's this graph look like? It's a point. Okay, and I graph it. A lot going on here. So it tells us that X is between 200 and 800. So let's change my window. Go from 200 to 800. Counting by 50. Graph.
Oh, just a little bit. Really hard.
Oh. Y'all have done this before.
No,
You've never pressed clear on the.
I know, I don't.
I
think
hit
have.
store.
I just don't be dumb. The calculator is screwed. I also observed. Also, it's 951 simulate.
Okay.
Road.
Huh. It's not graphing like it's supposed to.
Yeah, it didn't do that for me either.
Didn't graph for you either.
No.
Okay.
That is.
I think they just did it wrong.
Whoa, that is not what we saw. That is a 27.37.
That is not what we.
Yeah, that's what I typed in, 27.378.
It kind of.
You know what? I bet it is 27,000.
It is 27,000.
We don't want a comma. Okay, didn't help us.
Yeah, that one had like a scale of like 0 to 6,000 going.
Okay. That shouldn't be what it needs to be. Because the average is 514. The graph should go up to 514. I'll look at this and get back to you.
Less than that.
We'll come back to that problem. Some populations initially have rapid growth followed by declining rate of growth as indicated in this graph. One model for describing this type of growth pattern is logistic curve. So we have really fast growth and then it slows down. That could be caused by a lack of food source, right? You could grow a whole lot and then once you start running out of food, you can't grow anymore. So you kind of peak. Okay.
Or there's no room to expand.
Right. Example is bacteria culture that is initially allowed to grow under ideal conditions and then under less favorable conditions that inhibit growth, such as lack of food, maybe lack of light, maybe lack of space. Okay. A logistic growth curve is also called a sigmoidal curve.
The only sigmoid I know is the sigmoid fold.
On a college campus of 5,000 students, one student returns from vacation with a contagious and long-lasting flu virus. The spread of the virus is modeled by this. What's the maximum number of students that could have this virus? 5,000. So you see that's limited, right? Just common sense. No more than 5,000 students can get this virus. So that's all of them. Okay. There's the model. The college will cancel classes when 40% or more of the students are infected. Question number one, how many students are infected after 5 days? What do you do?
Plug 5 in for T.
Plug 5 in for T. Okay, great. After how many days will the college cancel classes?
More than
What does Y need to be? Okay, what is 40% of 5,000? So when 2,000 people have the virus, that is going to equal 5,000 divided by 1 plus 4,999 e to the 0.8 negative 0.8 t. I need to solve for t. What should we do? Okay, multiply by that. So 2,000 times 1 plus 4,999 e to the negative 0.8 t equals 5,000. And then what? Okay, divide by 2,000 gives me 1 plus 4,999 e to the negative 0.8 t equals 2.5. And then? Not yet. Subtract 1. 4,999 e to the negative 0.8 t equals 1.5. No. Divide by 4,999. E to the negative 0.8 t equals, I don't feel like doing that division.
3.00060012 e to the negative 1.
Beautiful.
Negative 4.
I'm going to leave it like that. Now what? Taking the natural log of both sides, negative 0.8 t equals natural log of 1.5 over 4,999. Notice that so far I have not rounded at all. Mathematically, don't round until you get to the end. Now what? T equals natural log, bless you, of 1.5 divided twice, that's it. Divided by negative 0.8. And that can just be keyed in the calculator. T equals what? Five thousand. It's gonna take 5,000 days. Natural log of 1.5 over 49.99 divided by negative 0.08. Or divided by negative 0.8. 10. Okay. So after about 10 days, we're going to cancel classes. Okay. And that's the end of the section.